Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year is 1629. The stage is set for a pivotal moment in the nascent development of mathematical analysis. The work in question 1629, Pierre de Fermat's method for determining maxima and minima. This wasn't merely a calculational trick, it was a conceptual revolution, a departure from the static geometry of Euclid towards a world brimming with change and flux. The intellectual climate preceding Fermat's breakthrough was defined by tension between the well-established methods of classical Greek geometry and the emerging challenges posed by problems in physics, particularly those related to motion and optics. Archimedes, centuries earlier, had made significant strides in calculating areas and volumes, employing methods of exhaustion which hinted at the notion of the infinite. Yet, these methods were cumbersome and lacked a general framework. The search for a concise and universally applicable procedure to solve problems of tangents, maxima, and minima was a persistent, almost obsessive, pursuit among European mathematicians. Fermat, a lawyer by profession, approached mathematics as an avocation, a pursuit fueled by intellectual curiosity and a deep appreciation for the elegance of mathematical reasoning. His work was greatly inspired by the investigations of Apollonius of Perga, whose treatises on conic sections provided a rich source of geometric problems. Fermat admired Apollonius' systematic approach to problems, and he sought to emulate this in his own work. He also drew inspiration from the works of François Viète, who had pioneered the use of algebraic notation, providing a powerful tool for representing and manipulating geometric relationships. Viète's symbolic methods allowed Fermat to express geometric problems in algebraic terms, facilitating the development of more general solutions. Fermat's core method, outlined in his treatise, rested on a remarkably insightful observation concerning the nature of maxima and minima. Consider a function, geometrically represented as a curve. At a maximum or minimum point, the tangent line to the curve is horizontal. Fermat realized that this condition could be exploited to develop a systematic procedure for finding the extreme values of functions. He essentially looked at the difference between the ordinate value at a point and a neighbouring point. The crux of his method involved a process that's akin to our modern concept of taking a limit. He introduced a small, non-zero quantity, now commonly denoted as e, that he used to perturb the independent variable. He then calculated the difference in the function's value corresponding to this small increment of the independent variable, dividing by e and setting the resulting expression equal to 0. Fermat found he could isolate the points where the function attains its maximum or minimum values. This process, though lacking the rigorous formalism of later calculus, provided a powerful and effective tool for solving optimization problems. The mechanics of Fermat's method might be illustrated with a simple example. Let's say we wish to find the maximum of the function that represents the square of x, or x squared. Following Fermat's method, we would first consider the quantity, the square of x plus e, expressed, mathematically, as the quantity x plus e squared. This would be equal to x squared plus the product of 2 times x times e plus e squared. The difference between this expression and the original function, x squared, would then be the product of 2 times x times e plus e squared. Dividing this difference by e, we obtain the expression that represents the product of 2 times x plus e. Fermat argued that since e represents a very small quantity, and since we are looking for the maximum, we can set the term related to e that is added to 2 times x equal to 0. Thus, through this procedure I determine that at the extremal point the value of x must be. The elegance of Fermat's method went considerably beyond its ability to solve concrete problems. It provided a conceptual framework for understanding the behavior of functions. By introducing the notion of infinitesimals, he paved the way for the development of calculus. His method could be applied to diverse problems, from determining the point where a light ray reflects off a surface to minimize its travel time, to finding the optimal dimensions of geometric shapes. It offered a unified approach to solving problems in both geometry and algebra, providing a bridge between the traditionally distinct domains. The immediate impact of Fermat's work was profound. His methods were quickly disseminated throughout the mathematical community. He communicated his ideas through letters and manuscript exchanges, rather than publishing in a formal journal, which exemplifies the relatively informal scholarly process of the time. His findings circulated amongst the leading mathematicians of the time, including Marin Mersenne, who acted as a central hub for scientific communication in Europe. The letters were like sparks, igniting a fire of further investigation and discovery. One particularly significant application was in the field of optics. Fermat's method provided a mathematical basis for understanding the law of refraction, which describes how light bends when it passes from one medium to another. Central to Fermat's vision of light propagation was the principle of least time. Light, he proposed, travels along the path that minimizes the time required to traverse the distance. Applying his method, Fermat was able to prove the law of refraction derived from this principle, providing a unifying framework for understanding both reflection and refraction. The immediate impact of Fermat's work on others was also tangible. The work of his contemporaries, like Descartes, was greatly influenced by Fermat's methods. Descartes, in his analytical geometry, laid the groundwork for the application of algebra to solve geometric problems, setting a stage for calculus, while the formal development of calculus is often attributed to Isaac Newton and Gottfried Wilhelm Leibniz. They both independently built upon the foundational work of Fermat, particularly his understanding of tangents and his methods for determining maxima and minima. Newton, in his early work, developed a version of calculus which he called the method of fluxions. His work contained many similarities to Fermat's. Leibniz also independently developed his own calculus. Both Newton and Leibniz recognized the power of Fermat's contribution, crediting him with paving the way for their discoveries. The reception of Fermat's work was initially enthusiastic, though not without its critics. Some, notably Descartes, expressed reservations about the validity of Fermat's method, questioning the rigor with which Fermat handled infinitesimals. This criticism reflects the ongoing debate about the foundations of mathematical analysis and the need for precise definitions and proofs. Descartes, despite his reservations, recognized the importance of Fermat's ideas. The debate served to stimulate further investigation and refinement of the method. Over time, Fermat's method underwent a series of revisions and deeper understandings. Mathematicians recognized the importance of establishing a more rigorous foundation for the concept of a limit, which underlies Fermat's procedure. The development of calculus in the late 17th and early 18th centuries provided a more formal framework for these ideas. The enduring legacy of Fermat's method for determining maxima and minima is immense. It marked a turning point in the history of mathematics, providing a powerful tool for solving problems in geometry, algebra, and physics. It provided the conceptual groundwork for the development of calculus and profoundly influenced the course of scientific thought. Fermat's work initiated a new era, moving from a static, geometric view of the world to a dynamic, flux-based framework, a world where change and relationships were the defining features. His contributions continue to resonate today, reminding us of the transformative power of intellectual curiosity and the enduring beauty of mathematical reasoning. His method is more than just a calculation, it is an elegant expression of a fundamental truth about the world, the underlying principle of optimization. The seeds of the calculus which underpin so much of modern science, from engineering to economics, were sown in 1629 by a lawyer with an abiding love of numbers.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.